Hey, well, welcome back. I hope everyone had a good weekend. Let's see. This is the beginning of the second week, obviously. We got about 15 weeks to go. Now, you might think that's a long way down the street, but before you know it, it's here. It's here. And one thing I've observed in teaching this class is that like most classes, the chapters we talk about build up onto other topics. So if you are having challenges here in the beginning chapters or any chapter, by all means, get some help. We do have tutoring. I gave you the link to the tutoring. If you need assistance with me, let me know. I can set up a Zoom time like an office hour. I don't have office hours, but if you need some assistance, I'm more than happy to help you out. Second of all, as you may know, I not only do I teach at GCC, I also teach at SEC, same class. So you're more than welcome to come on Fridays from noon to 2:40 is the class that I offered there. Jump in, same link, don't have to do anything and just hear the stuff. Normally they're like one chapter behind ballpark. I try to maintain both of them as close as possible. So right now everybody's done with chapter 1. So if you want to get a second batch of it, come on Friday, you're more than welcome. Also, all the videos that we got all the videos concerning all the topics, they're right there. So there's a lot of resources for you. And I know you have other classes, so you got to balance your time. Fully understand the needs. If you're working, you got family, all the above, you got to balance those needs to spend some time in all your classes. All right, so any questions at this point? Everybody know where to go on Canvas, where to get everything they need, okay? There's no like last minute, I don't know where to get my PDF files type of questions. It has happened. And so if you don't know, please send me an email or, let me know so we can take care of that. Now, we're going to start beginning with a little bit of math. And like I stated before, I may have mentioned that I said, if you can add, subtract, multiply, divide, you're good to go. All right. Nothing fancy here. We're not doing calculus, matrix, algebra, anything of the sort. Pure mathematics. Okay. Simple mathematics, nothing complicated. We're going to be doing a lot of conversion factors in here. We're going to use a technique to convert from one, say, metric unit to English unit. We're going to use this technique and apply it also to our chemical calculations, okay? And so I know you may have been taught a certain way to convert units from point A to point B. My suggestion is set those aside for right now and learn this technique, because it will help you with respect to the chemical reactions when we do calculations. Because eventually we're going to be able to calculate, if I start off with 10 grams of X, and how many grams of product do I make, or vice versa, okay? If I need 10 grams of product, how much material of starting material do I need? And we're going to use this technique of following, basically what it boils down to is follow your units, cancel your units out. And that's where the algebra comes in, just a little bit of algebra, keeping, we know the A over A, A's cancel, right? So you get up with 1. So nothing complicated, as I stated. So one thing, if you've not had a chance, let me share with you the website. I do have announcements up there. I hope everybody can see that. All right, so there are announcements. There is one announcement called metric units. I may suggest reading that. There is a file there that will help you with respect to converting units. We're going to have to learn how to convert from liters to milliliters to microliters to centimeters and so forth. So that will help you understand that concept a little better. There are this other one here having to do with what are called significant figures. We're going to talk about that topic today. So you may take a few minutes and read that information. Plus there's some other things in there. Yeah, scientific notation, how to utilize that with respect to a calculator, because we will be using scientific notation to do calculations of humongous numbers, big numbers, okay? And then there's some other videos and information there that you may, well, you know, it's pretty good enjoyment as far as I think, but I'm kind of biased being a chemist, right? About chemistry. Now, one thing here, another thing here, the last announcement, it deals with the different types of chemical reactions that we will talk about. And you would think with all the chemistry that's involved around us, and I mentioned this before, there's only 6 types of chemical reactions, and that little announcement talks about it, gives you additional information. So feel free to obviously read it. Let me back it up here. All right, so let me begin with today's chapter 2. Okay, we're going to talk a little bit about math skills. All right, so on the there is on the course website files, worksheets with respect to mathematics. Really, the more you can do, the better you become dealing with it. Okay, it's like a practice. So this page here, basically, don't forget about the text files on the course website to help you out with respect to calculating these, doing these calculations. Now, measurement, obviously, and measurement, we're going to be dealing with 3 types of measurements: a measurement of volume, a measurement of mass, and a measurement of length. Okay, and these measurements are going to have units. So we're going to be talking about units of mass, okay, units of volume, and units of length. Now, being in science, obviously, we deal with the metric system. So yes, we're going to deal with the metric system, but we're going to also kind of convert back and forth with the English units to help us with that technique of being able to convert back and forth using this process we call. There's a couple of names for it, but when I get to it, I'll let you know what we're talking about, okay? So metric units. Now, the one thing about this is when you use a number, a measurement with a number doesn't mean anything. When the book, one inputs as an answer, the book weighs 8. It's just a number. Are we talking about ounces? Are we talking about micrograms? Are we talking about pounds? Okay, so we need a measurement. We need a unit, and that's what's wrong with this comment. It says this book weighs 8. Well, 8 what? Okay, all right. So every measurement. Here's the thing that sometimes students have a hard time with, but every measurement, anything that you measure in length, anything that you measure in volume, okay, and any mass measurement has a degree of uncertainty. That last number, there is nothing out there, as far as I know, that is 100% correct. If you say I weigh 99.9 pounds, that 0.9 pounds, there's the uncertainty. That last number always has a degree of uncertainty, okay? Because every instrument we utilize is not that accurate. It really is. It depends on your measure, on your tool that you use. And some tools are more accurate than others, okay? Makes sense if you think about it. Is, let's say I'm measuring the length. I can use a ruler, 12-inch ruler, to measure the length of a room, or I can use a laser beam, right? Got these laser beams that you go in there and you got a lot of numbers. So obviously the laser beam has more accuracy, but even that laser beam, that last number has a degree of uncertainty, okay? Has a degree of uncertainty, which tells us that we're gonna have to deal with what are called significant digits, significant figures, okay? Whether some numbers are significant, whether some numbers are not significant, but with respect to accuracy. When I talk about significant figures, I'm not saying that number is worthless. I'm just saying that it doesn't play a factor with respect to a particular measurement, okay? Excuse me. So with respect to length, in the metric, we're going to be using these measurements up here that you can see. We have cm, mm, km. Okay, so we got centimeters, millimeters, meters, and kilometers. Those are the units, and most of the units that we're going to be using for measurement. Now we have one more that looks like a U. Okay, notice the prefix here, the prefix C, M, and the K. But this one here looks like a U with a little lip up front. This is micro. Okay, and so we have micrometers, centimeters, millimeters, and K for kilometers. Okay, now somebody's coming in. All right, so if we look at the prefix, if I asked you how many years in a century, right? You would say, okay, in 1 century, there are 100 years. So in 1 meter, there are 100 centimeters, right? If I said, all right, so for millimeters, if I asked the question, well, how many millimeters are there in 1 meter? Well, how many years in the millennium? Well, there are 1,000 years in the millennium. So there's 1,000 millimeters in 1 meter. And with respect to meters and 1 kilometers, there are 1,000 meters in 1 kilometers. Now there's one more here. I missed this one. If I were asked the question, how many years in a decade? You would say that there are 10 years in a decade. So the prefix decade, D, is 10. The prefix C is 100 for century. The prefix, the letter I should say, M for millennium is 1,000. And there's the K, there's 1,000 meters in 1 kilometer, 1 clip, okay? Now, every one of these conversion factors, because this is what they are, these are conversion factors, are a ratio, okay? And I can write these ratios, let me get some room here, in one of 2 ways. Where'd it go? There it is. And here's the thing about this, I want you to remember this, that every conversion factor, be it 100 miles per hour, that's a ratio in it, miles per hour. $50 an hour, that's a ratio, okay? Every ratio I can write with 1 or 2 ways. So I can take this one here and put decimeters in the numerator and meters in the bottom, okay? There's my factor. Or I can invert it and say meters on top and, oops, excuse me, that's a 10 decimeters. Okay, or I can put decimeters in the denominator. Okay, the point being here, and make sure this, you can see this, is this. Which factor I use depends on the units that I'm searching for, that I'm trying to get. The units that I'm looking for at the end of the day, it will always be in the numerator. So therefore, if I'm looking for meters, this is the unit that I'm going to take whatever I'm going to multiply. I may say 1,000 decimeters, convert that to meters. So if I say 1,000 decimeters, I'm going to multiply this by 1,000 decimeters because decimeters cancel. Now it's a little messy here, but I got some more coming at you. It's a little bit clearer here as far as display, okay? And so the point is that every conversion factor that we have, every ratio, be it a unit like going from staying within meters or going from inches to going from inches to centimeters, okay? Going from compound A to compound B is a ratio, and we're going to be able to tap into that ratio and keeping track of our units so we can get to the answer that we're looking for. Okay. All right, so let's go back to measuring for a second. So obviously, as I stated, every measurement, there's a degree of uncertainty, and every measurement tool that you use, there's a degree of accuracy. I think it's pretty self-explanatory here. You can see that the ruler, the white ruler, there's less increments. And so there's a degree, the white one is less accurate than the bottom one, the brown one, because there's more increments that we can get that last number a lot more accurate. For example, if we were trying to get a measurement, okay, and if let's say that line that we're trying to measure is this red one right here, okay, well, hopefully you can see here that the top one, it's that value is at least 4, right? And that we can't get any more accurate with the white ruler than the template. So we're going to have to kind of estimate that last number. And I don't know, I can call that maybe 0.3. You may call it maybe 0.2, that's okay. But that's the most accurate that we can get to the templates for the white one, right? So, because we know this is 4.5 right here, and we're going to estimate where that is. So we'll call it 4.3. There's that degree of uncertainty, the last measure. You may see it as 0.3. I may see it as 0.4. You're not incorrect. I'm not incorrect. It's simply because that degree of accuracy, that last digit, there's a degree of inaccuracy there because of the tool that we're using. Now, if we get down to the bottom here, we could go 4.3, and we can go further to the second decimal place, and I'll just call it 3.2, okay? So notice here that with the brown ruler, we can go to the 100 place, where the white ruler, we can only go to the 10 place, okay? Now, you may be tempted to want to use the white ruler and measure to the 0.32, but you can't because your tool is not that accurate, okay? So if I were to use the white ruler and display it as 4.32, like the brown ruler, that would be incorrect simply because the accuracy of my tool is not there to give me that number. All right. Okay, so obviously which has more uncertainty? The white ruler would have more degree of uncertainty. With respect to mass, there's a question. Let me see. Hi, I got your Fuchsia. Scott, yeah. Okay, no problem, I got it. All right, now with respect to mass, the masses that the units that we're going to utilize, this is just part of them. We got mg for milligrams. Guess what? In 1 gram, there, how many years in the millennium? 1,000, right? So we got m, the letter m again, like we did with millimeters. Here's milligrams, so there's 1,000 milligrams in 1 gram. Centigram, same scenario. Okay, that document I have on the announcement will talk you through all these prefixes. All right, so you can see hopefully that here we have 2 balances, and on the right we have a digital balance that we can very accurate. Okay, both in weight, mass, but the one on the right is a lot more accurate. Okay, we can go to the most standard balances like this one on the right. You can go to like the 4th decimal point, and the one on the left, you're probably going maybe 2 decimal points. Okay. Places, I should say. All right. All right, mass versus weight. Now we take it for granted. We kind of interchange the two, right? Because we're stuck on the earth, okay? But there is a difference between mass and weight, because weight is governed by the gravitational forces of wherever you're at, okay? Whereas mass is constant. The relationship between mass and weight are given as follows, where weight is equal to the mass times the gravitational force or whatever body that you happen to be on. So if we look at on the moon, the moon, the gravitational force is much less. Therefore, an astronaut, a person weighing 170 pounds here on Earth, is about 30 pounds on the moon, simply because of the gravitational force of the planet. However, the mass remains the same. If I take X amount of mass here, I take it to the moon, I still have the same amount of mass, okay? So that's the main difference between the two. We tend to interchange the two. Why? Because we're here on the Earth. So sometimes you may hear me say mass and weight. I was always, when I say mass, I'm talking about the weight, okay? Unless specifically asked to calculate one or the other. All right, so volume, here's some tools that we use to measure volume, but the units here are things like the capital L. Capital L is liters. Obviously you got K, guess what? Kiloliters, just like kilometers. So it's 1,000 in 1 kiloliter, there's 1,000 liters. There's that letter M again, millennium, M, 1,000. In 1,000 milliliters, that is equal to 1 liter, okay? And the same would be true for centiliters, we will use, and deciliters. All right, so let's see here. Syringes, you may be familiar with those you working in the medical field, maybe not, but the syringes, we have CC. Those units stand for cubic centimeters. That is an actual measurement of 1 centimeter by 1 centimeter by 1 centimeter, a volume, 3-dimensional, X, Y, and Z, okay? Hence we get cubic centimeters. Now here's our conversion factor that in 1 milliliter, that is equivalent to 1 cubic centimeter or 1 cc, okay? So obviously if you have 1,000 cc's, you got 1,000 milliliters. And you have 1,000 milliliters, you have 1 liter. All right. Now, here's something to help you out with respect to the English units. It's kind of, I like this little graph here because I always have trouble with cups and pints. So we're going to be dealing with gallons, the English unit. So we have the big G here, okay? Notice that under the big G, in the big G, there are 4 Qs. So that tells you that there are 4 quarts. Let me change the color here a little bit. 4 quarts in 1 gallon. Okay, 4 Qs. Within the Q, you see 2 Ps, that stands for pints. So there are 2 pints to 1 quart. Okay, and if you look carefully within the P, there are 2 little c's, and that is 2 cups in 1 pint. Okay, so that helps you to go from gallons down to cups if necessary. But the point again is that each one of these is a conversion factor. 4 quarts is 1 gallon, is equal to 1 gallon. I can write it with gallon in the numerator or gallon in the denominator. Now, a thing about using these as units, you might be tempted to take the inverse. Let's say we write it with 4 quarts like this, okay? And then you can write it with 4 quarts in the numerator, 1 gallon. Sometimes, didn't come out too good there. My resolution on my little pen here has been acting up. And so we got 4 quarts to 1 gallon. You might be tempted to invert that number when you're right here. Invert the 4, don't do that. Leave these ratios with the whole numbers whole. Just put them in the numerator or put them in the denominator, okay? Because if you invert it, it might throw you off down the road a little bit. So just keep the numbers as whatever value they are. All right, so this little tool kind of helps you out with respect to dealing with English units. Okay, now reading a volume, you, excuse me, when we read a volume when a liquid is in a cylinder, what happens, it forms this concave shape. Down here, we call that the meniscus, okay? And the way we read that is we read at the bottom of the meniscus. And so what you're looking at is, say you're looking over here. Okay, so, oh, sorry, my eye. Look at the bottom of the meniscus, and that is where you would read that reading for that volume. Also, the second thing to remember is be aware of your cylinder. Notice that 0 starts at the bottom of the cylinder, but we do have containers that 0 starts on top. So obviously that would change your value here. So be aware of point 1, where's my 0 point? So I know, am I starting at 20 or am I starting at 19 or whichever direction, okay? And then obviously then read your, look and see how many markings, like any ruler. The more markings, the more accurate. You can go to the 10th place, to the 100th place, or maybe even to the 3rd place or decimal place. So be aware of that. But the main takeaway here is with respect to liquids, you have a meniscus and you read the bottom of the meniscus for a particular volume. There are some liquids that the meniscus forms the other direction, okay? If that's the case, then do the opposite with respect to reading that particular volume. Okay, which brings us to the point about significant digits. Okay, now we have updated our shapes table, and I haven't uploaded. I just got it this morning, and so I will update the new shapes table. Let me pull it up, and in the shapes table is here. We have on the right side, we've added what are called the sig-fig rules, significant figure rules, okay? It's gonna help you out because we'll be using some significant figures where any measurement that we utilize and you present, you have to present it no more accurate. What this means is this, and it's a real straightforward concept. You can't report something more accurate that you don't have the tools, the accuracy of the tools to do that measurement, okay? Now, we all know we can do a calculation and our calculator spits out 10,000 figures, right? We might be tempted to write all the numbers in the calculator, but that would be incorrect. Why? Because we could have been using the tool that maybe we're only accurate to the 10th place. So so we're governed to report our number no more accurate than the least accurate method or numbers that we utilize to do that calculation. And that's what all the significant figures is all about, okay? So yeah, your calculator is gonna whip out 8 numbers, but you know, you're only good to maybe the 10th place or maybe the 100th place, okay? And there's some rules about it, and this kind of summarizes the little table there, summarize it for it. But we're gonna go into it a little more detail. And it seems complicated, but it really you just ask yourself 2 basic questions, and your answer is right there. I think the book kind of makes it more complicated than it really is. All right, so obviously. Here, with respect to accuracy, which we talked about, you know, a bathroom scale obviously is going to be less accurate than, say, a surgical scale, okay? And so they're going to have a surgical scale will have a lot more significant figures. So with this, okay, this is another example of the ruler we did before. You know, the top ruler, you know, we can, at the best, we can estimate to the 10th place, all right? So that top number could be, I don't know, call it, you know, 29.2. And that's it. We can't go anymore because that's the accuracy limited to the tool that we have to make a measurement. And the bottom one, we can go to the 100th place, okay? So obviously the bottom number, the bottom ruler has more digits, okay, has more accuracy. All right. So when it comes to the rules, I'm going to present the rules, and then I'm going to show you a little technique that you just ask yourself a couple of questions, okay? All non-zeros are considered significant. Now, here's the thing that I don't want you to confuse when I use the term significant. When we talk about significant, we're talking about the number of significant figures or numbers to present our data at the end, whatever we do with it, okay? It does not mean that it doesn't count in the magnitude or the value of the number that you have, okay? It does count, but it may not count with respect to how many digits you present your answer with, okay? So all non-zeros are significant. So this number here, 4,895.2, there are 5 sig figs, significant figures in that number, okay? The leading zero, so these are numbers less than 1. We just got leading zeros here, okay? So the first 4 zeros, they're not considered significant. All they are is decimal placeholders, okay? Decimal placeholders. So with respect to determining sig figs, they would not be a factor, these zeros. And so the only ones here that will count are 5454. Okay, so this number 0.0005454 has only 4 sig figs in there. Okay, so leading zeros do not count. Now notice something about the leading zeros that I'm going to give you here at the end. There's no integer in front of the leading zeros. Okay, no integer. The leading zeros, they don't count. Okay. Oops. All right. Now, when zeros are between whole numbers, digits, they count. Okay. So, for example, 3,050. Okay. The 0 between the 3 and the 5 count. They are stuck between 2 integers. Okay. So, but the other 0 after the 5 here is not considered significant. Now, the value, keep track of your magnitude here. What do I mean by magnitude? You know, when you look at a number, you know, you're in the 3,000 range, okay? And just because the last 0 is not considered significant, we cannot just simply drop that 0 and let it go away. Because if we do that, then look what happened to your magnitude. You went from $3,000 to $300, right? Okay, so don't do that. So be aware of the magnitude of the number that you're working with and not lose sight of the magnitude of the number. But with respect to being counted as significant or not, that last 0 does not count, okay? The next number, 0.00, while those are leading zeros, okay? That's the number 2 rule. So they don't count, okay? But the zeros between the 2 and the 1 are captive zeros, so they do count. And so this number here has 4 significant figures, okay? 4 significant figures. Now let me erase this. Now what does this mean? When, oh, we got one more. Okay, trailing zeros. Okay, zeros after a decimal point and after an integer count. Okay, and if you look at this, okay, this number here, the 0.0, those are leading zeros. Again, rule number 2, they don't count. But then you might think, okay, the last 0 after the 8, okay, does it count? Well, First of all, it's in front of an integer. It's in front of 8. There's an integer in front of it. And guess what? There's a decimal point in that number, anywhere in that number. That answers your question right there, whether that 0 is significant or not. If for that 0, if there's an integer in front and there's a decimal point anywhere in that number, that 0 counts. Let's try it over here. Same number, and ask those same questions for these zeros right here. The first 3 zeros. Is there an integer in front of these 3 zeros? No, they don't count. You're done. These do not count. Ask that question for this 0. Is there an integer in front of any integer in front of that 0? Yes, there is. There's an 8. And is there a decimal point anywhere in that number? Yes, there is. So I got 2 yeses. That means that 0 counts. Therefore, we have 3 sig figs for that number. Okay. You can ask that question for any of these other problems we just did. Look it up here. Go up here. Leading zeros. If let's say you didn't know what, you forgot about the leading zero rule. Okay, ask the question. Is there an integer in front of any of these 4 zeros? No. Okay, we don't go any further. These zeros do not count as being significant. Okay, look at this 0 right here. Okay, question number 1. Okay, let me write it over here. 3050. We know that these zeros, the zeros that are in between integers, automatically count. You don't have to go any further. Okay, so that 0 counts. Question is this 0, the last 0. Okay, ask the question. Is there an integer in front of it? Yeah, there is. Okay, got 1 yes. Now, is there a decimal point anywhere in that 0? Answer is no. That means this 0, the last 0, would be considered insignificant, and therefore there's only 3 sig figs here. See? See how that works? Okay, just by asking that question for any 0. Is there an integer in front of it? Is there a decimal point in front of it? Okay. Now, what can happen now, if I take that 3050 and I force it and I put a decimal point in front of it right there, guess what? All those zeros count now. Okay. All right. The moment I put a decimal point in there, I made that last 0 count. All right, so let's, excuse me. And so here we have 28.00. Again, ask the questions. You can see that number has 5 sig figs. The result is this. Notice that we determine now 5 sig figs, 4 sig figs, 3 sig figs, 3 sig figs, 5 sig figs. Now, when we multiply and divide only, okay? When we multiply and divide only, okay? If I were to take this number with 3 sig figs, if I were to say, take 0.0880 and multiply that or divide it by, let's say, this number, okay, that number, then my answer should only have 3 sig figs at the end. Why? Because I'm going to multiply or divide by the least significant number, which is this one right here. Okay, and this is how that works for multiplying and dividing only. Okay, your answer should have no more sig figs than the number that has the least number of significant figures, which is basically the least accurate. You can't be more accurate than the least accurate number. Okay, and that's multiply and divide only. I emphasize that because when we add and subtract, different rule, simple rule, we follow decimal places. When we multiply, divide, we follow significant figures, okay? But either way, it comes down to being no more accurate than the least accurate digit. Okay, but don't mix and match the two, the two rules: multiply and divide separate, and add and subtract. Now we have exact numbers that play no factor with respect to how, if you have to multiply, divide, or add or subtract with these numbers, and they're exact numbers. And so things like, 14 people, 3 feet per yard, that's a conversion factor. It's exactly 3 feet per yard. It's exactly 14 people. There's exactly 100 pennies in a dollar. 5 iPads, a 12-pack, that's exactly 12-pack. Even a dozen, there's 12, unless it's a baker's dozen, then we're talking 13, right? But those are exact numbers, and exact numbers do not play a factor in determining your final answer, okay? Because they're exact numbers. Things that are measured, here we go. Any measurement, mass, length, and weight. Well, did I say that twice? Volume, excuse me. Any of the three, anything you measure, anything that you use a tool to measure is not exact. It's that last digit that is a questionable, okay, degree of uncertainty. And so for numbers like 7 inches, 200 pounds, 10 ounces, anything that's measured is not exact, and then could be a factor in your final answer. So, 7 inch, we're looking at 1 sig fig. It could be a factor if you're multiplying that number with something else, okay? All right, so any measurement, anything measured is not an exact number and could be a factor. We have 3 conversion factors that and we'll get to here in a second, that we give to you that get you from metric to English. And the 3 of them, length, mass, and volume. 2 of them are measurements. 1 of them is considered exact, and I'll show you here in a second which one. So the one that's considered exact is not used in the calculations in determining how many sig figs, okay? So here they're asking you here, how many sig figs in the following number? So let's take a look at the first number, 5.05. Well, this one's straightforward. Why? Because that 0 is stuck between 2 integers. You don't have to go any further. Any zeros in between 2 integers automatically is significant. We know that all in numbers 1 through 9 are significant, okay? So this has 3 sig figs. This number has 3 sig figs. All right, let's take a look at 1200. Ask itself the question for the zeros. Question number 1 for the zeros. Do they have an integer in front of it? And the answer is yeah, they got a 12 in front of it. Okay, so that's 1 yes. Then you ask yourself the second question, is there a decimal point anywhere in that number? Answer is no. So anytime if you get 2 yeses, those zeros are considered significant. If you get 1 no, not significant. So there's only 2 significant figures in that number, okay? The next one here, 0.02020. Well, we can break it up, and through the rules, we know that leading zeros are not considered significant. But let's assume for a moment you forgot the rules. Let's go through each set and ask the question. The first 2 zeros, okay? Is there a decimal point, an integer anywhere in front of those 2 zeros? No, therefore not significant. All right. The 0 in the middle between the 2's, automatically we know trapped zeros count. So that 0 will count, okay? And then finally, the last 0, okay? Is there an integer in front of that number? Yes. Is there a decimal point anywhere in that number? Answer is yes. So that last zero counts. Therefore, that number has 4 sig figs. Okay. Now, if you start seeing here, if I were to multiply at this point or divide these two numbers, if I were to multiply or divide these two numbers, my answer should have no more than 2 sig figs at the end. Okay, see how does that work? How that works? If I were to multiply or divide this number with that number, our answer should have no more than 3 sig figs. Okay, again, our answer cannot be more accurate than the least accurate number. And counting the sig figs tells us which one is the least accurate. We're multiplying and dividing only. All right, so the next one here, again, these are leading zeros, 0.0005. And so those leading zeros, there's no integer in front of them, so they do not count as significant, okay? That doesn't, so there's only 1 sig fig. It doesn't mean that they are not of value, okay? I can't overemphasize this. They are of value because they're holding our decimal point, okay? But they're not of value with respect to our final answer if we have to do any mathematical function using that number. So if I were to multiply or divide this number and this number together, then our answer should have no more than 1 sig fig. And we're going to talk about how to get to that 1 sig fig answer. We're going to do that by rounding your number, okay? Which I'm sure you're familiar with, but straightforward procedure. All right, so next one, we got 50. 50, you know, obviously integer counts. The 0, we're not sure. It's got an integer in front of it, but there's no decimal point anywhere. So 50 only has 1 sig fig, okay? But the moment we put a decimal point, now we added two zeros, so we got 50.00. Those zeros count now because we have an integer in front of all. We got the 5 in front of the 3 zeros, and we have a decimal point. And so you can see that the 0.00, just adding the last 2 zeros, makes it a lot more accurate than just 50. Okay. Obviously, 123.45, everybody's an integer. There's no question there. They all count. They're all significant. And then finally, the last one, we have 3 sig figs for that. Okay. Okay, this here kind of just summarizes for you. And they ask the question, is there a decimal point in front of the 0? And is there a integer in front of the 0 and a decimal point anywhere? And then it tells you, okay, it counts, and that doesn't count. So numbers like 1001 have 4 sig figs. Numbers like 1000 have 1 sig fig. Numbers like 1.01, we're looking at 3 sig figs, okay? And we do this because we're going to do something mathematically to these numbers, and we need to determine the least accurate number because that is how our answer will be presented. I know you might be thinking, okay, well, my calculator says I got 8 digits here, you know, 1.46810. That gives me accuracy. But remember, you're not that accurate. You didn't use a tool with that accuracy. If you use a tool with that much accuracy, yes, you will be correct to present your number with that degree of accuracy. Okay. All right. So we get into rounding here. Okay. So because we're going to tap into the rounding, how we do it, and then that allows us to present a number and answer the correct number of sig figs or the correct number accuracy. Okay. The rules are pretty straightforward. What we do is you find a number that you need to round. Okay. Whatever number that may be. Okay. So you find it. You look immediately to the right, the number to the right of it. We don't care about the number 10 digits down. We don't care about the number after the second one to the right. That makes no factor here. Because I know sometimes you're once tempted, well, if I round this number, I can do a cascade effect. No, no, no. The number immediately to the right. If that number is less than 5, okay, the number that you're going to round stays the same, okay? If that number is equal to 5 or greater, then you pump up that number, you need to round up to the next number. For example, we need to round 5.4. So we need to round it to 1 sig fig, one significant figure. Right now there's 2 sig figs. So we're going to round it right at the 5, okay? We look immediately to the right. Look at that number, look at the magnitude of that number. It's a 4, it's less than 5. Therefore, the 5 that we need to round stays as a 5. So we present that number as 5. That's our answer, okay? All right, so we do the same with, say, 5.5. So we're gonna go round the final answer to 1 sig fig. So I mark the number I need to round. Look at the neighbor, because it's greater or equal to 5. So therefore the 5 gets kicked up to 6. So then we present the answer as 6, okay? So we don't, like I said, we don't care about what number is down the road. If we need to round a number here, we only care about the one immediately to the right, okay? And that determines whether that 5, here's the other thing to remember, that number you're gonna round, it's either gonna stay the same or go up 1, okay? Doesn't go down 1. Stay the same or go up, okay? So this number would never be 4, okay? 5.4 would not be 4. It's either going to stay 5 or go up 1 number. That's another error that I've seen sometimes, that they round down. There's no rounding down. It stays the same or rounds up 1. Okay. All right. Now, excuse me. Here's the thing I mentioned earlier about the magnitude. When you get ready to round numbers up, be aware of the magnitude, the value of your number that you're going to round. See, right here, you're in the 5,000 value, 5,000, 5400. And it says to round it off, round to 1 sig figs, okay? So that means that 1 sig fig is the first number. So that 5 is going to be either stay at 5 or kick up to 6. So we do the rounding rule and we look at the neighbor, and the neighbor is 4 and it's less than 5. So that 5 remains a 5. Now, once we do that, that 4 we set to 0. But don't forget about the other zeros, okay? Because you're in the 5,000. I mean, think about, put a dollar bill in front of there. Which would you rather have, $5,000 or $5, right? You see how you change the magnitude by dropping the zeros? And so one way to remember this is let's start over here, 5400. If we had a decimal point there, okay, let's say that's where a decimal point will go, right? Thing to remember is any numbers before the decimal point get converted to 0. Any numbers after the decimal point get dropped. You don't need it because you don't change the magnitude by adding zeros at the decimal point, okay? In fact, you change the number of sig figs, right? And so, but the thing to remember is before the decimal point, be the decimal point be there or not, you know where it would be, okay? All numbers get converted to 0. Otherwise, you end up changing the magnitude and you end up presenting your data as 5. in which, remember, you're at 5,000 range, not at the $5 range, you're at the $5,000 range, okay? So be aware of your magnitude when you finally present your data, that you do not drop any zeros before the decimal point, which then changes your magnitude. Actually the value of your number, okay? For example, let's do a couple here. It says round to 3 significant figures. So starting at the far left, you count across and you count 3 positions, okay? And so here's the one. So the 3 significant digit position would be right there on the 3, okay? So then that means that we're either we're gonna round it off here. And so either that 3 stays 3 or it goes up to 4. And we look at our immediate neighbor, okay? Again, we don't care about what's down the road, immediate neighbor only. And we see that it's a 7, which is greater than or equal to 5. That means that that 3 becomes a 4. And then we just drop all the numbers after that, okay? And so our answer is, that's our position. We're looking at the neighbor, okay? That tells us that the 3 goes to 4. Now you may be tempted to do this. Now, who can tell me that you added the 2 zeros to replace the 7 4? What will be wrong with that particular answer? Or is there anything wrong with this answer? You see what I did? Let's see, instead of dropping the 7 and a 4, I added a 0. What have I done by adding 2 zeros? Yeah, anybody know what, tell me what I did wrong? Or maybe I didn't do anything wrong. Did I do anything wrong by adding 2 zeros?
You changed the significant figures.
Exactly. I changed the sig figs because now I have how many? 1, 2, 3, 4, 5. 5 sig figs here. Okay. The problem said I need 3. Okay. And so not only did I change the sig figs, I made it more accurate. Okay, right? By adding 5 sig figs. Okay, so be careful. And that's what I mean. Any numbers after the decimal point, just you drop them off. Get rid of them. You don't need to worry about them. Any numbers in front of the decimal point get converted to zeros. Okay. You remember that? You got no problem. So this would be totally incorrect because I changed the assignment. I created 2 sig figs. All right. This one again, 3. We want to go 3 sig figs. Same thing. Go over from the far left. 3 sig fig position, which would be the 6, okay? So the 6 is either going to remain 6 or it's going to go up to 7. So we do the rounding rule. We see that the immediate neighbor is less than 5, so that 6 remains 6. 2 things. We see that we got a 2 in front of the decimal point. So that 2 gets changed to 0, right? Because otherwise, we're going to change the magnitude. If we drop that 2, we'll create, I'll show you here, it creates 760, and look at the magnitude. You're at the $7,000 range, okay? So you don't want to change the magnitude of your answer. Oh, let me clear this up here. I'm a mess here. So that's the position we're going to change. And so we convert the 2 to 0. We don't drop it, okay? Because it's in front of the decimal point. And if we drop it, we change the magnitude to $716 versus $7,160, okay? All right, here we have this one. we find, remember the leading zeros, they don't count as significant. And so starting with the 1, we count from the 1 to the right to find the 3 sig fig position. And the problem here is 3 sig figs. We could have selected 4 sig figs and, you know, whichever 2 sig figs or even 1 sig fig, but the procedure is the same. So that's our 3 sig fig position. That means that we got to either that 1 stays 1 or goes up to 2. We look at the neighbor and the neighbor's less than 5. Therefore, we can simply drop the 1, the 5, and the 4. And our answer is 0.00131. Okay. And we're doing the rounding here because you could have, this is your answer. This is, you know, you might say, this answer you got here, maybe you multiplied or divide numbers that one of the numbers had 3 sig figs. Okay. So, you know, you did a multiplication or a division with some number that gave you, had 3 sig figs. So you knew that your answer cannot be more accurate than the number you did the mathematical function with. Okay. And that's what we do. We do the multiplication. Your calculator is going to whip out 10,000 figures. We got to find where to truncate it. And then that's where you present the answer. Okay. All right. The next one, again, we find the 3 sig fig position starting from the far left. So we're going to do the 9 here. We look at the neighbor, which is 2. Again, the decimal point will be right after the 5. That means that those 2 numbers of 2 and 5 get converted to 0. Why? Because we are at the 24,000 range. Okay, and so our answer is 24900, and we don't truncate it, right? We don't drop the 2 and the 5. We change the 2 and the 5 to zeros. Otherwise, your answer would be 249, which is a lot different than 24,000. Okay. Key points about rounding is, you know, drop numbers after the decimal point. Once you, after whatever is there after the decimal point that they're going to be dropped, you just drop. That doesn't change the magnitude after the decimal point. In fact, if you add zeros after the decimal point, you increase the number of sig figs like I demonstrated earlier. And numbers before the decimal point, you convert those to 0. Okay. If you don't, you change the magnitude. And so, you know, you're in the 24,000 range here. You don't want to be in the 249 range. Big difference in the magnitude. And that's where the most of the errors occur, is dealing with those numbers in front of the decimal point. Do I drop them? Well, yeah, you drop them, but then you convert them to zeros. So you won't change the magnitude. Okay, now up to this point, multiplying, dividing, our answer should have, you count sig figs, okay? You work on sig figs. When we add and subtract, sig figs do not play a role, okay? So we'll keep the 2 apart. Add and subtract, we're dealing with decimal places. And in both cases, whether we're dealing with sig figs or decimal places, we're dealing again with the fact that you can't present your data with more accuracy than the least accurate data that you had to begin with. Okay, that's what all this stuff's all about. Just presenting your data with the correct accuracy. Okay, so you find the answer. Your final answer must not will have the same decimal places as that number with the least number of decimal places. Okay, and we're going to use the rounding procedure like we just did to get us to that point. That doesn't change. Okay, so let's take this number, 13.5478. Okay, and we're going to subtract. Now we could add here to make a difference. Same procedure, same rules, but we're going to subtract 11.20. Okay. So you can see that the first number has 4 decimal places. Okay, everybody agree on that? You got 4 decimal places here. And the other one has only 2 decimal places. It's to the 100th place. And so your answer should have no more decimal places than 11.200. Okay, so you do the math in your calculator. No numbers, don't truncate. Here's the other aspect. Don't do any rounding. Do the full math in both multiplying, dividing, or adding and subtracting with the numbers you're given. Okay, I know in what has happened in the past is people round them up, round the 13.5478 and move it to 2 decimal places. And no, don't do that. Just do the math with the numbers you're given, and then when you're done, deal with the rounding. Okay, so we get the full, we're subtracting, we get the full 2.3478. Okay, and then we see that we're only going to go, no, we're not counting sig figs here. We're only counting decimal places. We can only go 2 decimal places because that number had the least number of decimal places. So we're going to truncate at the 4. And then we use the rounding rules like we've been doing. You can see that the neighbor is 7 is greater than 5, greater or equal than 5. So that 4 becomes a 5. Okay, so our answer is 2.35. Okay, which again is not more accurate than the least accurate reading, which only had 2 decimal places. Okay. So our least accurate reading only had, this could be an example of, I could be measuring a rule, or maybe doing a measurement with the top number, maybe a laser instrument, something that gave me some very accurate numbers. And then the bottom one, maybe I'm doing with a tape measure or something. Okay. My answer at the end of the day cannot be more accurate than the one I did with the tape measure. Okay, even though you might be tempted to think, well, I got the laser there, it gave me a better number. Well, no, because your other number is not that accurate. Okay. All right. Now, this is what I mean about don't mix and match sig figs. Okay. Why? Sig figs, when it comes to adding and subtracting, have no factor here. Here's the thing. Who can tell me how many sig figs are in this number right there?
There's 6 significant figures.
6, that's correct. How about down here?
There's 4.
There's 4 right here, 4 sig figs. And then our answer?
3.
3. So you can notice that there's no correlationship between sig figs. 2 of our problems had 6 and 4, and our answer has 3. Okay. If we were multiplying and dividing, then if we were multiplying these 2 numbers, these that we just did, then our answer should have no more than 4 sig figs. Okay. All right. So don't correlate the 2. Don't mix and match the 2. Adding and subtracting, count decimal places. Multiplying and dividing, focus on sig figs. Adding and subtracting, focus on decimal places. Okay, back and forth. Don't mix the 2 because they have no correlation. But they both amount to not presenting your final answer with the least number of accuracy that you use in your numbers to do any type of measurement. Okay. Was that clear as mud? I don't think I said that right. But I hope you get the gist of what I'm saying here. You cannot be more accurate than the least accurate digits that you have. All right. So focus on decimal places when you add and subtract. Okay. This here is just a reminder as far as your places to kind of remember where you are with respect to magnitude. Remember, you don't want to lose your magnitude. You know, those are examples of dropping the digits before the decimal point and changing the magnitude, okay? Now, when it comes to multiplying and dividing, okay, a couple of things you gotta remember here. When we add and subtracted, remember the units we use, we had the one with feet. We can only add and subtract like terms, right? So we were subtracting feet. Not the same case when it comes to as far as units, when it comes to multiplying and dividing, because multiplying and dividing, we got a little algebra going on where either units are going to combine or they may even, you know, cancel out. And so you be aware of your units. For example, you might think, well, what am I talking about? Well, this problem here, if this was in inches, obviously if this 11.20 was in inches, we could not subtract that. We have to convert somebody, right? Okay, we got to put those in like terms. We would have to convert the feet to inches or the inches to feet, okay? When it comes to multiplying and dividing, we don't have to worry about that. They're letters, they're algebra. We're gonna multiply them together, or we're gonna add them together at the end, or they're gonna cancel each other out, or they're going to multiply and give you like m times m. We are taking 3.546 meters and multiplying that by 1.4 meters, okay? And so here, we got to look at sig figs, okay? So point one, we look at sig figs. So how many sig figs do we have in the first number here? What do we got? Anybody tell me that?
4.
We got 4 sig figs, that is correct. And your second end, how about the second one?
2.
We got 2 sig figs, okay? And so that means at the end of the day, our answer should only have 2 sig figs, okay? Then the other aspect to remember, look at our units. We got meters times meters, okay? And so meters times meters, what would that be answer-wise?
Meters.
No, if you let's
Square?
meter squared, that is correct. Okay, meter square. Okay, because this is when the units are like units, you know, it's like it's like m to the 1 power times m to the 1 power. We simply add the exponent. Okay, and if we were to do this one more time, that would be meters cubed. So like the one earlier, it was centimeters times centimeters times centimeters. That gave us cubic centimeters, okay? And so we got apples times apples. What do we get? Apple square, right? Times apple, apples cubed, times apple, apples to the 4th, okay? And if we get apple times orange, anybody know what that unit would be? I'm using crazy units to show you that whether you use crazy units or meters, it's the same thing. What units would I have if I multiply apples times oranges? I know I have a fruit salad.
Apple orange.
I'd be apple orange. Okay, apple / orange. Okay, and if I was apple times apple, then it'll be apple square. Okay, and if I got apple times apple, I got an apple pie, apple cube. Okay, all right. So these are units that we're going to remember when we're multiplying to keep track of. Now, if we are dividing these units, let me very quickly. Let's say we have meters square, and we're going to divide by meters. What would be the answer? Okay, another way to look at this, remember I said apples times apples. Well, meter square, I can write m times m, right? Wouldn't these m's cancel out? Anyway, so that leaves me with m's, right? And so if I had,
M&M.
pardon me?
I was saying M&Ms.
And if m's, yeah. It would be 1 m at the end because I got one of them canceled out, okay, when I'm dividing. Now, obviously, if I got a, if I had, okay, we'll get more on this, okay? But this is straight basic algebra that you really got to kind of keep track of this to help you out when we get to units and we start conversion factors, because we're going to be using the units to get us from point A to point B. And if you set that up properly, I guarantee you 99% that you got the problem set up properly by following the units. I can't say 100%. Why? Because I don't control the calculator that you push the number in there, right? Because sometimes the wrong number gets calculated because the wrong number got inputted into the calculator. But if you set up the units properly and be aware that you can cancel like terms, be it M, be it apples and apples, be it, you know, and I have an extreme example that I'm going to run through on Thursday, which is some crazy units. You might think, what does this got to do with chemistry? It had nothing to do with chemistry. It has to do with the thought process that I can take whatever units I'm given and I can calculate from one set of units to another set of units. If I have the correct conversion factors and if I set the problem up correctly, okay? But I'll show you that one on Thursday. All right, so let's go back to this one. So we're gonna multiply. We just calculated that the one with the least sig figs is the 1.4. So our answer should have no more than 2 sig figs, plus our units here would be square meters, okay? And so we multiply it out and our calculator will whip out 4.9644. Don't do any pre-truncating, you know, rounding off. Wait until you are done before you round anything off. And then because we have 2 sig figs here, where our 2 sig fig position is the 9. And so that 9 either is going to stay 9 or go up to 10. Okay. And so here, we look at the neighbor is 6. That means that 9 goes to 10. So we're going to carry the 1 over. So we have 5.0 meters square. Okay. Again, 2 sig figs on our answer, which is the same number of sig figs that our least accurate digit has. In this case, 1.4. And then don't forget the corresponding units. Now we could have multiplied this, and this could have been centimeters, cm. Our answer would have just simply been the same, but our units would have been centimeters hyphen meters. Okay. Whereas in this case, when we multiply and divide, we don't have to change units like we did with adding and subtracting. Multiplying, we just combine them, and our units would be presented as cm hyphen meters. But in both cases, in this case, both of them are both in meters. Okay. All right. What we got here? 3 minutes. All right. Well, we got what's called scientific notation. If you haven't had an opportunity to play with this in your calculator, you may want to, do that, because what this does is it allows us to express extremely large numbers, okay, or very small numbers as given there. Sometimes it's difficult to type that. Now, let's say you needed to multiply these two numbers or divide or even add them, whatever. You need some mathematical function in calculator. Sometimes it's inputting that number on top. Some calculators won't accept it. And so, but it would accept it in scientific notation format. And so what this does is this format allows us to input these humongous numbers, because we do work with some very, very large numbers. In fact, there's a number that we'll be using called Avogadro's number, that if you were to count one number a second, so you start counting now, 1, 2, 3, 4, 5, 6, etc. You'll be done in a few thousand years. That's how big that number is. Okay. And so we will be using humongous numbers. So let's I went over the time a little bit. Let us jump onto this chapter on Thursday, and then I'll go over that example of we'll finish this one up, and then we'll get into some calculations and using that method and how to go from one unit set to another. And other than that, let's stop it here. So, okay. Any questions at this point?